Alright everybody, this video is about the beginning conversations of camshaft design and some of the issues you run into when it comes to figuring out what camshaft is best for your engine. Stay tuned because in another episode we're going to go into racing and how to choose a camshaft and why. Thanks for watching, y'all. Please like, share, and subscribe. Alright, now make sure y'all speak up, because we won't film you, but I want you to speak.
So the question was, how does the manufacturer compensate for the extra load on the engine?
Yeah, you got a car with an air conditioner and the factory idle is 750, 800, whatever it is. Why? Number one, is it set that low? Number two, when the AC comes on, you have a big current draw because of your radiator condenser fans, the blower fan inside. If it's got dual AC, you have a rear fan. The compressor clutch is drawing current, and all that extra current draw loads down the alternator. So now the alternator is harder to turn, compressor is harder to turn, and the engine was already down to 750, 800 RPMs idle, and you just loaded it down a lot more. So within 30 seconds, the vehicle shuts off because it's idling too low. So what is done to compensate for that?
Raise the idle.
So every time I turn the AC on, I'm going to jump out, pop the hood, and turn the idle up with a screwdriver?
Well, no, it would be computer controlled.
Exactly. With what?
PCME or a PC
The idle air controlled motor. Okay? It is a motor. It's a stepper motor. And it is nothing more than a controlled vacuum leak. Alright? What does a controlled vacuum leak mean? If I open up, say, a 3/8 diameter hole in the intake, that's going to allow a large amount of fresh air to come into the intake, which is going to make it idle up very high, also make it go lean. But if I control that with a motor that will in and out over this hole, stop.
Yeah.
I can control the air coming in the intake and have a controlled vacuum leak, which adjusts my idle. That's one of the easiest and simplest ways to do it. They've been doing it that way since the very first fuel injection with throttle bodies on American cars. So with a carburetor, we don't have that option. We don't have an idle air control motor. So how is it done? What would be, in your mind, a simple way to have, when you turn the AC on, something makes it idle up? You turn the AC off, it disengages. What's an easy way to do that besides you jumping out and turning the idle screw up? Think about all the options you have available to you in the world.
Well, I would want something to be able to know when I hit that button that I am now introducing an additional load to it. And so at that point, I would also appreciate if it would send like a
Let's make it easy.
higher air
What
fuel
does-
mixture.
What does a solenoid do? Excuse me, Coke Zero. a solenoid, right? It takes electrical energy and turns it into mechanical motion, basically. So if we take a 12-volt supply, say an AC switch, and when that switch is engaged, it sends 12 volts to a little tiny solenoid that just goes boom. And it has a bolt in it with threaded adjustment that I can mount to the carburetor right in front of the throttle linkage. Turn the AC on. Hits the throttle linkage. Turn the AC off. It disengages. And if it's idled way too high, I can turn the bolt in and back the idle down with the switch engaged. Alright? Back in the old days, we called them hot switches, but it's basically a little solenoid that you mount to your carburetor that will manually, when you turn the AC on, it mechanically hits that throttle linkage and holds it at a high RPM because of the increased load on the engine. Okay? With fuel injection, the idle air control motor that does the controlled vacuum leak from the start, it just lets in more air. It lets in more air, the engine RPM's higher, computer's controlling the air-fuel ratio so it's not going lean, and it does it in a moment's notice. The modern day ECMs are like, I don't know the exact number now, but at one time I heard they were 1,000 times a second monitoring certain systems. ABS being one of them, airbags another one. But the modern ECM now is so fast, it can really control that air-fuel ratio. I mean, in minuscule seconds, right? It's very accurate. Very accurate. So all that leads me to this conversation I want to have with you today, because it's going to tie into everything you've had thus far. Okay? Thus far, meaning from the start to today, you're going to get, I think, an understanding of a lot of stuff dealing with why the factory does what it does, and why racing does what it does, why street racers do what they do. Hopefully this will be eye-opening. So, that's why I wanted to go ahead and record this. Alright, so basically what I want to talk to you about today is tip of the iceberg, but why factories do what they do, why racing engine builders do what they do, street rods do what they do. All these people do what they do in their choices of induction system and camshaft timing and for example, air conditioning like we're talking about right now. Why do they do what they do? So, you understand that an engine has two valves. The ICE engine, internal combustion engine, right? Takes petroleum fuel of some type, takes that chemical fuel, turns it into mechanical motion, and that's what we've been doing a long, long time. It's basically an air pump, so the more air we can make it pull in, and the more air it can push out, then the more power it makes. It varies between power it makes and pound-feet of torque that it makes. The two are, you can have an engine with a lot of one or a lot of the other, and you're trying to make it blend. For example, for all the guys who are stuck on the fact that torque wins races, I've never seen anybody race a locomotive engine. If torque wins races, why don't you get that engine and put a big, giant, tall gear to it and see how well you do? You know, come on. It's not. There's a balance. And in America, Americans like their power. And so the factory is being challenged with, not to be offensive to anybody, but not to be more European, meaning everything is much smaller in European countries. The engines are smaller. But mostly that's because the cities over there, and I've been over there in 12 different countries, the cities are a lot of times, not always, but a lot of times smaller because they're older. They were founded way before America, so they've been building on top of those areas much longer than we have. Now, there are cities in America that's becoming the same. It's absolutely, we don't like it as Americans. We like our open spaces. But so you build and adapt to that environment. But here, we still like the big cars, the big power smoking, all of that. So how do you get the best of both worlds? I have a lot of hot rodders will ask me, hey, I want this much power, I want it to sound this way, and I want AC. Well, if you're putting in a factory supercharged fuel injected engine, that's a piece of cake. If you're trying to go old school with something from the 50s or 60s or even 40s type platform, meaning 440 Dodge or big block Chevy, small block Ford, whatever, if you're trying to use that platform with a carburetor and you want 600-700 horsepower and air conditioning, it starts to become a little more challenging. Why is it challenging? Because the nature of making power with that old platform. For example, the cylinder heads is the biggest issue with the old platforms. They did not flow very well. I've said many times in some of my older videos that port shape is as important as port size, and port size is huge. It's a big deal. What do I mean it's a big deal? Basically, when I'm doing a cylinder head, when the factories are not necessarily close to this, we're going to get into that. But when I'm trying to make an engine, the guy says, hey, I want all the power I can get, but I want you to run this platform, right? The valve size will dictate a lot of times how big I make the intake runner. Anybody that goes in there with a porting tool, a grinding tool, and just goes to town in the intake runner and the exhaust runner without any thought of the size of the valve, most likely their stuff's not going to be that great. And it doesn't mean that they won't see big flow numbers, it just means it'll get passed on the racetrack. There has to be consideration for the size of the valve. Why? Because if you have a shop vac vacuum cleaner and you've got the hose, if I have, because the vacuum cleaners industry, they're always bragging on how many amps their vacuum cleaner has. This 6 amp shop vac, or I got the 10 amp shop vac. What they're telling you is when you turn it on, your meter on your house goes like this. It's consuming that many amps. What is amps? Amps is the volume, right? Voltage is your pressure behind it. So if you have a vacuum cleaner that consumes 10 amps of current, that means the motor on it is fairly large. If the motor on it is fairly large, then it's probably going to pull pretty good vacuum. So we have all that established, and now you got your hose there, and it's 3 inches diameter vacuum hose, and it comes all the way down to the end of the hose, and it's a tiny little opening right at the end. Okay, so that will have high vacuum suction, but the volume is not be that great. All right, that would be a large engine with a very small head. You with me? Now let's take a vacuum cleaner that has 2 amps of current, a tiny little motor, and you've got a 3-inch hose on it, and at the end of the hose, it flares out to 5 inches. That would be a example of somebody going in there and porting a head really huge with the wrong valve size. What will I not have with that scenario?
Good vacuum.
I won't have any suction, will I? It might not even pick up toilet paper.
You might feel the air.
Yeah, you'll feel the air passing by your hand, but there'll be no velocity whatsoever. Velocity is what carries the air and fuel. And velocity has momentum and inertia to it. I've said this before. Okay? I want velocity because that's what's going to take the fuel and pull it out of my carburetor, or as the injector fires, that it grabs that fuel in the air and mixes it and drives it into my cylinder. Okay? I need enough velocity, and I've heard some weird things said one time about low lift flow numbers. I don't remember who said it. It's not really important, but here's what I want you to understand about it. I need enough velocity so that when the piston is traveling upwards, it's still going in the bore. You say that's not possible. Yes, it is possible. In fact, yeah, we do it all the time. What you don't want is the tiny vacuum cleaner motor with the giant hose that has no suction. Because what happens is your piston will start dictating when it flows in the pores. How's that? What do you mean by that, right? If the valve is open and you have no velocity, the piston will push air or pull air in the port. I want the port to overpower that. Now, go back to the scenario with the 10 amp vacuum cleaner and the tiny little hose at the end, right? That big engine, that 450 cubic inch, 500 cubic inch engine, 600 cubic inch engine, whatever it is, that big engine, okay, I've got a lot of velocity, so when I step on the gas pedal, it accelerates really hard. And then all of a sudden it's like I get to 3,800 RPMs, and you feel the engine just like it's just not, it's done, right? It's still RPMing, but it ain't making that speedometer wrap up there. There's not enough volume to feed it. I've said this many times, and I don't know if everybody understands what I mean by it, but when you shorten the crank stroke, you're making your heads more efficient. All right? Because the stroke length dictates how long I pull on that head and port combination. If I have a very short stroke, I will not need a ton of cam duration. Why not? Because it's down to bottom dead center and already back up like that. And if I throw a bunch of duration to a tiny short stroke, I won't have any cylinder pressure because the valves are not closed long enough for me to build any cylinder pressure. Well, what makes that bomb big or small, right? If we take gunpowder and pour it out on the ground, and as a kid I used to do this all the time, we would light it and you just get a big woof and a smoke cloud. But if you take that same amount of gunpowder and put it in a very tight package, compress it, and light it, you now have a bomb that's lethal. So what does that represent? Compression. The more the compression, the tighter I squeeze it, the more bang for the buck I'm going to get. In the same token, I'm not going to have cylinder pressure if I've got the valve open so long. So the crank stroke dictates how much duration I should have. That's one of the major influences. I should word it that way. So you will see a lot of these factories lately will use a large stroke engine or larger stroke engine and a small bore. That stroke really influences engine dynamics. It is, yeah, and the cylinder heads are more efficient with a bigger bore because you're unshrouding the valve. But, for example, you take an LS3 head, an LS3 head flows a lot of air. Well, if you look at the strokes they're putting underneath them, they've got a lot of head there for that engine, and it performs really well. And you take that same head, put it on something like a 3.5 inch crank, and that head's capable of turning in the high 7,000 RPMs. So my point being, all of this has to do with cylinder pressure and vacuum and what we're going to talk about today. Now, in the terms of air conditioning, we've got a calculation, a compression calculator pulled up. This is optional for dynamic compression. So they're asking you, the question was, you have two types of valves in your engine, right? Intake valve, exhaust valve. And it could be a 4-valve, 2-valve, it doesn't matter. There's an intake and exhaust valve. The numbers we use when we design camshafts, there's 5 numbers. There's the intake valve closing and opening, exhaust valve closing and opening, or say it the other way if you want, and load separation angle, and then intake cylinder. So I guess there's 6. The first set of numbers, the IBC and IBO, IBC, EBO, EBC, which is short for what? Exhaust valve opening, exhaust valve closing. You have those numbers at 50 thousandths lift, and you have those numbers at what some of us call advertised. And not to make it complicated, because I'm not trying to get real complicated on that, but it's measured at 6 thousandths lift for some hydraulics and 20 thousandths lift for solids. But the point is, you have advertised and at 50. What does that mean? Very quickly, to put all the world on the same sheet of paper, everybody back in the day was measuring their cams at different points. So Chris may have a cam that says, I'm 230 duration cam, and I may have a cam that's 200 degrees duration, but when you actually put them on a wheel and measure them, my cam's larger than his, and it's because everybody was measuring them at different points. So they got together and decided, we got to put this on a national scale or world scale that everybody's on the same sheet of music. So what they decided was, okay, once we lift the valve 6 thousandths, we'll start counting from that point. Does that make sense? Once we lift the valve 50 thousandths, we'll start counting the duration from that point. And that way everybody's on the same sheet of music. So that's what they did. And it's asking you here for the intake valve closing at 50, all right? So I want you to put in there, Devontae, 54. Yep, 54. All right, let's calculate it. 9.4 to 1. Dynamically, 7.27. All right. Now, people with not much track experience, okay, racetrack experience, will look at these calculators, and that's what they base their whole life on. Their whole cam theory is based on that calculator. Well, the one thing you can base on that calculator is it's going to give you the dynamic compression. Now, what is the difference between static and dynamic? Come on, guys. Static. What's static?
Static
It's
is
not moving.
no movement.
Right?
Dynamic is.
That's right. So statically, right? When you build the engine, the volume above the piston, when it's at bottom dead center, compressed into the cylinder head when everything's at top dead center, including the gasket, is your static compression. And that is based on 100%, meaning if it was a perfect world. The problem comes with the engines are not always at 100%. So let's look at the dynamic part. It's telling me that with the camshaft I've chosen, based on the static compression of 9.4, if I run a camshaft that size, my dynamic compression is going to be 7.27. Now I want you to follow me here because all this matters, right? So what is the camshaft I've chosen? I haven't given you any numbers, have I? I've only told you the intake valve closing. Alright? So I told you the intake valve closing was 54, right? Now I'm going to throw the rest of them. So we got intake valve opening is 12. Let's see. Well, now I can't see. So we've got 57. And then closing is 15. Okay. That's at 50. Now, remember those numbers I was just talking about the 6,000ths lift?
Yeah.
Okay, so these are those numbers, or what a lot of people call advertised. So this would be 41, 83, 86, 44. 41, 83, 86, 44. Okay, so that's IBO, IBC, EBO, and EBC. Alright? And this is at 06, or what some people call advertised. Now, how many of you understand that? Anybody? What do these numbers represent? They represent, now the camshaft turns half the speed of the crank, right? Okay, so what they represent, if this is our cam gear, this is our crank gear, right? They represent, if you were to have, well, basically represent crank degrees. Now, why do they represent crank degrees? Because that's how we measure it, right? We measure in relationship to the piston. That's just like if you have a object riding a cam loop, right? You may have a certain size object on the cam that's riding that cam load. What do I do with it? I got one right here somewhere. And here it is. Yeah, this will be good. So you have a object that rides that cam load. Now, if I shrink this object, right, the contact patch is much smaller. So the camshaft has to turn further to make it move. If I grow this object up to a certain point, it will start moving sooner to a certain point. Once it gets to that certain point, you can change as large as you want. It's not going to grow anymore. It does not change the numbers of my camshaft. It's just where it picks it up. You follow me? Mm-hmm. So in other words, it might pick it up dead center. It's still going to read the same duration and lift. Or it might pick it up on the edge. Still going to read the same duration and lift. However, what it does change is where it picks up in relation to where the piston is. If I'm picking the cam lobe up faster earlier, then that's going to be as if it's advanced on the crank. if I've shrunk it down so far that it's just barely touching dead center of this, then it's going to be as if it's retarded on the crank. If you're trying to compare the two, okay? Now, so these numbers, this would be, this side at 50 would be, I'm not getting those numbers until I lift this lifter 50,000. That's when I'll start, and that's when these, I should be at these crank degrees when this happens. Okay? And then at 6, this will start to lift about 6 thousandths, then I'm getting and checking these numbers, okay? So that's what they are. It gets difficult for people who don't do this every day to understand this. But this is in reality what's actually going on. Now, we have a static of 9.4 to 1 compression. And we have a dynamic of 7.27 to 1. All right? Now, Devontae, go back down, or can you hit the back arrow? See what that does for you? Okay, yeah, cool. Now, go up there where it says cylinder head volume. No, don't do that. Where the stroke is 3.48, I want you to change that to 4.0. And hit calculate. All right. So this was with a 3.48 stroke. Now, with a 4-inch stroke, our static jumped to, is that 10.65?
Yeah.
Compression, statically. Dynamically, it just went to 8.31 to 1. Okay? This is a fairly large camshaft, by the way. You don't know that yet because all you're seeing is opening and closing numbers. Okay? Now I'm going to show you something here. Let's keep going. Now, once you go hit the back arrow again and change the bore size to 4.155.
4.155.
4.155. Hit calculate. Now that just changed my compression by going to a bore to 11.41 to 1. By boring the block 125 thousandths, my compression ratio jumped almost an entire point. It jumped 0.8. Okay, that's quite a bit. Statically now, we are 11.4. All right, what's the dynamic on it? 8.89. What kind of drawing was that? Holy crap. Okay, so now we are 8.89 to 1 compression. Okay? Just so you understand, we're going to go back to the original 350 stats. So hit the back arrow, Devontae. We're going to go 4-inch on the bore and 3.480 on the stroke. And I'm going to give you a new cam number.
3.48. And then the cylinder bore was just 4.
Okay, so now I want you to put in, on the intake valve closing, I want you to put 30 and let's see what it says. Okay. Check this out, guys. So now we've changed all of these numbers and our intake valve closing. I know this gets a little bit wonky, but intake valve closing is now 30. And with the 350, okay, the 72 cc's, 4 inches bore, 3.480 stroke, intake valve closing at 30, my static compression is now 9.4 to 1. Dynamically, it is at 8.49. Okay, so dynamic, static. So what are you trying to get at? With a steel iron head factory car, you're not racing it, you're just driving, hauling a boat sometimes, hauling a trailer, going to work every day. This is pretty much the norm, and this is what the gasoline in that pump is designed to run. Follow me? Now, I want you to look at something. With a large camshaft, we have to be at 11.4 statically to get to 8.89 to 1 dynamically. Does that mean that I can run that much compression on pump gas with that camshaft with aluminum head? Shouldn't have no problems. You know how big that cam is? Pretty large. It's in the mid-high 260 duration at 50 with 300 and something advertised duration, 700 lift. If you hear that car run, it sounds like a dragster. I mean, it's but it takes that much static compression to get that much dynamic compression so that we can run pump gas, the same as this 350 that makes 300 horsepower. And that would make 750 horsepower. Now, going back to the vacuum cleaner scenario and all that, right? These numbers control when the valve opens and when the valve closes. You understand? You'll notice on the compression calculator, it wants to know when the intake valve closes. That's all it asks for. Was the static, cylinder head, bore and stroke numbers, and then when does that valve close? What I'm after is velocity to continue to pour into the cylinder as the valve is shutting. You say, what do you mean velocity? I don't have a good example that I can easily throw around. Well, yeah, I do. No, I don't. This is an old 2-liter head off of a 2000 Ford Focus. It has the dual intake ports. We'll talk about that. There's I think a 1.73 intake valve, and I don't remember the exhaust valve. But I want, when that valve is shutting, remember, intake valve closing, I want the air and fuel to still be coming in as the valve is closing. When the valve starts to open, I don't want the piston shoving air and fuel up in my intake. And you know what? In a racing scenario, high performance scenario, the piston is coming up as the valve starts to open. What happens to my intake vacuum if I have very poor velocity and the piston's coming up as the intake valve opens? What's going to happen to that airstream coming in?
It's going to get pushed back
It's
out.
going to get pushed back. What's my intake vacuum going to do?
Drop.
It's going to drop. Exactly. We're going to have reversion. So, what we know and figured out a long time ago was that if we can have a good high-flowing exhaust system, when the intake valve starts to open, what's closing? The exhaust is closing. So if we can get the exhaust stream that's leaving, hopefully quickly, if we open these two at the same time, as the exhaust is leaving, it's pulling in air and fuel. That's called scavenging. That's called overlap. Overlap is if you have something you put on top of it. I've overlapped it, like a shingle, like these are butted together. This is overlap. We're not talking about the valves overlapping physically. We're talking about the scale of crank degrees. The exhaust opens and closes on its own little deal, and so does the intake. And overlap is when they merge together on the big scheme of things. Meaning, as the exhaust starts to close, my intake valve is opening, they're open at the same time, so they're overlapped on the scale. The more overlap I have, there's a really good chance my performance increases. But what else is happening when it's overlapped? I'm not building pressure. You see what I mean?
Mm-hmm.
So if I have a ton of overlap, what do I need statically to counteract it? Compression. This is where people miss the boat. But this is where the factory, they understand it. If I have a lot of overlap, what else do I have? Now think about what's happening during overlap. There's a lot, actually, but think about it from a factory point of view. If I have overlap, I have unburnt fuel in my exhaust. Well, if I'm factory, what am I fighting against, like all the time?
The government.
The government. EPA laws. Can't be having that, because EPA will see it, they'll do their exhaust test and go, oh, you failed. You can't put that car out. Or we're going to fine you, or whatever, whatever they do. So, if I'm got multi-millions of dollars at my disposal, and I can make a phone call and have anybody I want sitting at my door tomorrow, what am I going to do? I'm going to develop an engine where I can change the overlap at a whim. Which is what they did. Because we used to use EGR, now we use valve timing. So what do you mean? Well, if I widen my lobe separation angle so that I don't have any overlap, I don't have unburnt fuel going in my exhaust, I have very high vacuum. Why do I have high vacuum? Think about what we talked about. You see, because this isn't all there is to it. That's all the compression calculator talked about. But that ain't all there is to it, because what have I eliminated in this conversation with just using that? I've eliminated the exhaust. And the exhaust is doing something. It's working behind the scenes. So if I widen the overlap, I widen my lobe separation angle, and I decrease my overlap, okay, now I do not have scavenging going on. But because my valves are closing, and I'm not losing cylinder pressure in different places, I have more cylinder pressure right now. Now here's the thing. It solely will rely on the intake valve and port shape, intake runner, velocity, volume. It's going to much more be reliant on that design when you don't have overlap to make any kind of power. Because the overlap did what? It scavenged, and it assisted in filling the cylinder. So now it's got to rely on that, and usually because in performance you can hardly ever have the best of both. It's hard to do. You either have really good torque on the bottom or really good performance up top. It's hard to get them together with the same overlap, you know what I mean? So what they've done, and keep your emissions clean. Remember, that's the whole deal. So with a wide overlap, let's say LSA being 125, okay? The lobe separation angle is 125 degrees. That means when that intake valve gets to peak lift, measuring it at the crank with a degree wheel, remember how we did that? Peak lift on the intake valve, it's going to have to go 125 crankshaft degrees before it gets to peak lift on the exhaust. Crank degrees. Okay, that's overlap. That's lobe separation angle. Excuse me. Now, with that being said, I have no unburnt fuel. This is say hypothetically going in my exhaust. So my exhaust is clean. I also do not have the two valves open at the same time. So I don't have any scavenging going on. I have no cylinder, what we call a little misfire going on that causes that nice thumpy racy sound that we all love. I don't have that going on. And I don't have, most likely, I do not have reversion happening. And with the modern EFI that's using a MAP sensor in the intake, it's very sensitive to intake pulses. It does not want to see the vacuum going down and up at a rapid pace. Okay, even though modern EFIs can handle it now. The older EFIs, well, they just didn't know what to do. But if I get a smooth idle and you see a steady draw on the vacuum for the MAP sensor, that engine is going to have high vacuum, good throttle response, everything it needs, good clean emissions. But once it probably gets to 3,000 RPM, it's a dog. It don't make any power. So the factory says, okay, well, what we'll do is use the computer to change our events. We can change these. How do we change it?
Changing your valve time.
Changing my valve timing. I'm changing my lobe separation angle and intake center line, exhaust center line, moving them closer together. When I move them close together, I get scavenging, I get a lot more RPM performance. Because the EPA requires emissions at idle. Now, I don't know all the ins and outs of the technical laws, but I know I'm old enough to have done this long enough that when we did inspections on cars, you check them at idle. You check them at 2,000 RPM for a couple minutes to heat them up, to warm them up, to get the converter up to temperature, catalytic converter. And then you put a tailpipe sniffer in the exhaust and you let it idle for up to 2 minutes. And if it was really clean and the emissions machine was in good shape, within usually 30 seconds, it spit out a report saying you're good to go, you can get out of there. It always checked it at idle. There was a time when they were going to put each car on a dyno and check it for NOx, but they never did that. Now, the EPA knows that if the check engine light is not on, these cars are so good, as long as that check engine light is not on, it is clean. And I was at a GM seminar, and the guy from Chevrolet said that the EPA proposed that Congress wouldn't let it happen. They proposed a law that said if your check engine light came on, you had up to 50 miles to get it to a dealer, or they would satellite turn your vehicle off or make it go into limp mode.
Good luck.
The GM guy told us that at the seminar. He said the EPA proposed that, but Congress said, heck no, you lost your mind. You know, I mean, unbelievable that people even think that way.
I mean,
You
they
could
would've
cause
taken-
an accident.
Oh, absolutely.
You could call people to get really mad and show up at your house.
They
Okay, I
would've-
think they forget that.
They would have easily taken a third of the cars off the road. though.
Oh yeah, oh yeah.
That's not right.
But one thing I have noticed is that the vehicles today, I don't have or see as many frivolous check engine lights like I used to. Now the EVAP systems are still an issue, things like that. But anyways, this subject takes weeks. This subject, people want to simplify it. It's not simple. You, especially as a newbie, right? We'll just say person who really is not not studied this and does not have racetrack experience, if I was to tell you to, hey, pick me a camshaft that will turn 8,500 RPMs, and I want my power band from 5,000 to 9,000, and just let me know what my numbers are. You wouldn't have the slightest idea what to put down. All right, so what happens is guys like me who grew up at the track, I know this. I'm just going to throw these out there. I know this right here. So I know that I can buy any load that somebody makes. And that load may be, and again, the at 50, because it's a point of measurement, might be 240. And in this particular case, at 20, might be 240, we'll say 280, just to say, okay? 280. Now what is this right here, okay? This is crank degrees duration. And what does that mean? That means that is how many crank degrees that valve is open. It's open at 50. If you measure, if you lift the lifter 50 thousandths, okay, start counting from there, you'll get to 240 degrees and it should be 50 from closing. This one, you lift it 20, you're going to go 280 degrees and it'll be 20 thousandths from shutting. I'm talking about the valve, the lifter rise, okay, because ratios now change it at the valve. Don't forget that. All right, but this is what we saw growing up. So you have a cam that's 240, 280 on the intake. This marker is sticking, messing me up here. And you have one that said 246, 286 on the exhaust, with a lug separation angle of 106. Let's just call it that. Okay? This is what so many people are familiar with. And you know what? After you go to the track long enough and dyno test engines long enough and see what they do long enough, this starts to make sense to you. But if you put this in an opening and closing scenario, you'll start to understand these numbers. But if I said, hey, I got a 240, 246 cam in on 106, and it runs really good at the very end of the straightaway, but it doesn't have a lot coming out the corner. Okay? The response is, well, why don't we tighten it? Why don't we, what's your intake center line right now? Oh, well, I've degreed it in. The intake center line, ICL, is on 106. So, he's like, okay, well, why don't you put it in on 102, see what it does. Okay, so now we're going to advance it 4 degrees, plus 4 degrees, so now it's on 102. And he comes back to you and says, well, yeah, it did move the power band a little bit. It didn't feel as strong everywhere. But it did come in a little sooner. Or he could say, my gosh, it changed the whole world of this engine. It's a completely different animal now. All right? Getting back to the point at hand, you've got a guy that contracts you that says, hey, I want a good engine that's got a little lump to it that makes a ton of power, and I want to run air conditioning. Compression comes into play. These numbers come into play. Velocity comes into play. Volume comes into play. Okay? So how do we choose the right choice because number one, the man's got to stop when he hits the brakes, and power brakes requires vacuum. We need at least 10 inches of vacuum. Okay? So these are things that the factory, people like me, people like future you, has to deal with to get this thing correct. So if I want to run the AC, I have a unique problem now. Tell me, what's my unique problems now with air conditioning? You know what they are, so what's my unique problems? It's power drawn, right, from the compressor, from the fans. That loads down the alternator. Compressor itself, pumping the refrigerant, that loads down the engine too. The blower fans inside the car load down the engine. And I asked earlier, why do we idle the cars at 800 or whatever in that area? Why do we do that? Because if you idle them up super high, what do they do when you put them in gear? Right? You don't want to tear your transmission out. You don't want to make the car undrivable. You don't want to be sitting in a Walmart parking lot and put it in reverse and kill some person walking behind you with a buggy. You want to be good and nice to your equipment. So, you have it idled at a lower rate. But because it's idled at a lower rate, when I put a load on it, if we don't have something to counter that, it's going to shut off. Now, what all comes into play there too? Let's say the guy wants 700 horsepower, like he said. Let me ask you something. If you have an intake like this one, for example, let's say all these go to the same motor, hypothetically. If you have an intake like this one, okay, versus an intake like this one, which one's going to have more vacuum? I mean, just based on looking at it, right? You think that one had more vacuum? Okay, let's do it this way. What are these here? My intake runners, right? Get a good eyeball. Okay? All right, how about these? Now which one's going to have more vacuum? What creates vacuum? Which one's going to have more velocity? At idle. Okay, at idle.
At idle?
Yeah. Which one's bigger? This one's obviously bigger, yes?
That one's larger, right?
So, think about your vacuum cleaner scenario. The big motor with a little tiny hole, or the little tiny motor with a big hose, right? They both are wrong. So what we want is the motor with the right size hose. Now, this here, remember this is all scenario wise the same engine. If this intake is much smaller, which one's going to have more vacuum and more velocity? This one. Because now I've got this larger component pulling through a very small port. That's going to create what? Faster airspeed. You with me?
Yep.
Okay, so you now know that intake manifold, right? If I have a really small intake, my airspeed increases because I've lost what? Volume. So the guy's wanting 700 horsepower. Is that intake going to make 700 horsepower? No, it won't. Will that one? Yes, it can. So I need that intake to make 700 horsepower, but I have a unique issue with it's a much larger intake, so my vacuum's going to be inhibited some. I'm going to have to figure that in. Okay? Also, same scenario, right? The engine is pulling through this little 2-barrel. You have all this volume, the cubic inch, pulling through these 2 ports. That's all it has. All right? Is it going to have more or less velocity than this one. By the way, these are all wasted, junky carburetors off the boats. This one's got 4 holes, that one's got 2. So which one's going to have a higher idle velocity? Idle. The 2 barrel. Because it has less space for all that cubic inch airflow to come through. Okay? So at idle, this 2 barrel will see much higher velocities and probably a little better vacuum than this one. It's the scenario, guys, where you're pumping a vacuum on a bottle that you poked a hole in the top. If I got a tiny hole, it's going to pull the bottle down the vacuum. But if I make a really large hole, am I ever going to see vacuum? That's what you're dealing with here. Tiny hole, big hole. Okay? No reversion, probably some reversion, depending on how big my cam is. So then how do I compensate when I turn on the AC? Remember the little pot switch was talking about? There it is. It's grounded through the body of the case. 12 volts. Put 12 volts to that. That thing kicks out. You see how it does that? Kicks out. Idles it up. Boom. And in this particular model, this is the old Ford model, you can adjust how much it idles it up or down by this screw right here, this bolt. The one that Holley makes, this whole, in GM style, you have a bolt you turn that will raise or lower the idles. So, modern EFI has the same problem. Don't think they don't. Here is Ford's answer to making some kind of power with a tiny cylinder head. You can see it's only a 2-valve head. Well, then why do I got 2 different shaped runners here going into it?
Get maximum airflow.
Yeah, so you see what they did was they've got about a 2-inch thick plate that mounts in front of this. And on the one side, this is called a variable intake rudder design. Alright, so we have variable camshafts, actuators. We also have variable intakes. What they do is, at idle, they have a throttle blade in front of this, and it stays shut. When you stomp it to the floor, it opens this blade up. Now you have all of this pumping fuel and air into the cylinder. So there's your volume. Your velocity is there because you have one tiny little runner here that's small. It makes good velocity. So for just drivability from a stoplight, whatever, you got good velocity, good torque. Need some power to get around somebody? This blade opens up, and now you have all of this to take in fuel and air. Variable intake. It's brilliant. It really is. I don't think I'd have made my runners look like that. I don't understand their thinking with the whatever that is, but
Space saving.
one has got the injector in it, and one is just airflow. But at any rate, that's how they did it, and it works. So velocity and volume, it's a must. And you have to choose, in the old days, one or the other. And with the modern technology, we're able to get both with the variable intake design, variable intake runner, cam variations. But what I wanted you to see was, if you're going to put AC on a car and have these other attributes, little sounds, big power numbers, good vacuum, the load that the AC with the fans and everything puts on the engine, how do you compensate for that? Why do we idle a car at 800? All of that comes into being a good engine and an engine builder and technician. And there's so many things. Compression, right? If I'm gonna put a really large cam in a car, I gotta have static compression behind it. If you've never driven an engine that had 6-to-1 compression or 6.5-to-1 compression dynamically, you will see that it will not get out of its own way. It's a piece of junk because they did not design it. In fact, I just helped a guy the other day who statically built a 600 cubic inch big block engine and put a cam in there for a 12-to-1 engine. And his cranking compression was 130 pounds. And it won't RPM past 5,800. It falls on its face. And I'm like, you don't have enough. Your static is way too low, so your dynamic is way too low for the cam that you put in it. So all that comes into play. But, all right, who has a question right now? Bring it back, sing it back to me.
No.
Come on, Devontae. What's up, man? All right, brother. Well, let's take a break.